Hi everyone, my name is Michael and this is my partner Jonas alongside our group members James, Will and Hui together on the Spaghetti Bridges Structures 1 project. Bridges are structures that help us cross obstacles like rivers, roads or valleys by carrying loads from the deck down to support each end. No matter the size, whether it's a simple plank over a stream or a massive highway crossing, every bridge shares the same purpose, to safely carry weight across a gap. There are several types of bridges like beam bridges, arch bridges, suspension bridges, cable-stayed bridges, cantilever bridges, and truss bridges. Each manages compression and tension in a unique way.
Exactly. For example, beam bridges bend under load, arch bridges carry compression along a curved shape, and suspension bridges use long cables and tension. Truss bridges, which we focused on, are made up of straight members forming triangles. These triangles make the structure strong and stable because they spread forces evenly through tension and compression. That's why truss bridges are still used everywhere from railways to highways.
Within the truss family, we looked at three main designs, the Pratt, Howie, and Warren trusses. After comparing them, we decided to use the Pratt truss for our spaghetti bridge. In a Pratt truss, the diagonals lean toward the center and mainly carry tension, while the verticals carry compression, since dry spaghetti performs much better under tension than compression. This design suited our material perfectly.
That's right, the Pratt truss was patented in 1844 by Thomas and Caleb Pratt and quickly became one of the most popular bridge types worldwide. Its simple layout, predictable force pattern, and efficiency made it ideal for both real bridges and our small-scale model. You can see famous examples like the Fort Atkinson Bridge in Iowa and the Guilford Quarry Bridge in Maryland, both built with the same structure.
Our bridge spanned 360 millimeters with a height of 90 millimeters and a width of 60 millimeters to match the test frame. The bridge was divided into 4 equal 90 millimeters panels with vertical posts and diagonals leaning toward the center. The loading plate hung at the midpoint just like the testing setup required.
We made the bridge slightly taller than a flat beam design because increasing the height reduces bending stress and the risk of buckling in the top chord. We also made the bottom chord thicker since it carried tension, while the top chord, which carried compression, needed to stay straight and well braced.
For materials, we used Cole's Simply Spaghetti and Sally's Quick Super Glue. Even though the glue dries quickly, we learned that using too much can slow down curing. So we applied thin layers and let each section cure overnight.
We also discovered that moisture and the temperature really affected the spaghetti strength. If it gets humid, the spaghetti softens and bends more easily. To avoid that, we built indoors and stored parts in dry conditions between sessions. One of our early pieces even cracked because the diagonal member had a small bend and a glue ridge that pushed the load off center, showing just how delicate the material is.
Before the testing, we used a 2D free truss analysis calculator to stimulate how forces moved through the structure. The results showed that most of the longer diagonal members were in tension, which was ideal for spaghetti, and the top chords were in compression. The color diagram made it clear how the forces balanced out across the structure.
This modeling step helped us understand where to reinforce the bridge and on which members would be most vulnerable. It was a good example of how digital tools can help predict real-world behavior, even for small-scale projects.
Next, we tested our bridges using the standard testing apparatus. The bridge sat freely on 2 bearing plates, and we slowly added load through the middle joint until failure.
We tested 2 bridges with the same geometry. The first bridge held 7 kilograms before breaking, while the second bridge failed at 7 kilograms. Even though they looked almost identical, the difference came down to build quality and precision.
In the 7 kilogram bridge, everything stayed square and stable as the load increased. The top chord remained straight and both trusses worked together until the very end.
But in the 3 kilogram bridge, there was a slight twist or racking between the 2 sides. The top chord began to bow sideways early on and some glue joints were uneven, creating off-center forces. These small imperfections caused early buckling and failure, which shows how sensitive structures are to alignment.
From this project, we learned several key things. Keep compression members straight and short, use thin, even glue layers to avoid off-center loads, add diagonal or X bracing between trusses to reduce twisting, and always ensure the load plate is centered for even force distribution.
We also realized how closely this small-scale model reflects real engineering. In real bridges, precision and alignment can make the difference between safety and failure, exactly like in our test.
Overall, our Spaghetti Pratt truss bridge demonstrated how classical truss principles still work at any scale. The 7 kg bridge showed that careful construction and accurate geometry lead to a much stronger structure.
Despite our time and material limits, the project helped us understand how forces move through real bridges and how design choices, precision, and teamwork can make all the difference.
On behalf of our team, myself, Jonas, James, Will, and Hui, thank you for watching our Spaghetti Bridge presentation and have a good day.